Give me a second. All right, I think we can begin. So, I was approached by Randa last night regarding this, and due to the missing speaker, I had to stand in for him. So this is a bit of what I've been doing in the past month or so. Not for my day job, this is like on the side that I do on the weekends and stuff, but I hope you enjoy it. But we're gonna be making fake Pokemon in Tensorflow. Well, you can make it in any machine learning library, but because it's Google, we have to use Tensorflow. So, so maybe you want to ask questions before we start. What's a Pokemon? I mean, really? Everyone knows what a Pokemon is, right? Who doesn't know what a Pokemon is? Okay, thank you. What's a TensorFlow? Okay, or what's TensorFlow? It's Google's computational graph library, so you can do parallelized computing. But really, the power that's, or the hype that's making it really, really awesome is machine learning. And I think it's a pretty nice tool now, especially since they've included some of the new features that we're going to look at today. Yeah, some pictures. So pardon me if the slides are a bit boring or a bit sloppy. I literally had this morning to do it. Yes, so what are we doing? Okay, so we want to create a Pokemon by looking at our own Pokemon, or fake Pokemon, by looking at existing ones. So there's like a bunch, oops, not yet, not the story time yet. So there's a bunch of Pokemon over there. Can I bring up my pointer? Technology, look at that. So we've got a bunch of Pokemons there, and they're images, right? They're basically images of things, and we can use some techniques to maybe approximate these images, but we don't want to generate the images themselves. We want to generate things that look like the images, right? So think about it as like copying an artwork, or like doing your own thing on top of an artwork, or copying, Picasso or whatever. So how are we going to use it? We're going to use something called GANs. Hands up if you know what a GAN is. Few people, okay. So GAN is like the technology that's making this happen. Particularly, it's a variation of GAN. So GAN is an older technology that is developed in 2014. The paper came out in 2014. Nowadays, people have iterated over it, and we've got so many different variants. Today we're going to look at a particular variation of it called DC GAN. But for a lot of people, the term GAN, or generative adversarial networks, kind of scare people for a bit. And I kind of want to get a story out so that it makes you kind of think twice about, it's not really a scary thing. It's actually quite intuitive if you think of the analog. So, story time. In a world. No, I'm kidding. So imagine a city where there's, a normal city, but the population of this city is a bunch of criminals and a bunch of cops. Okay? So the city has like money laying around in the department stores and everything, and these bunch of criminals, every day they try to somehow trick the cops. They want to make more money that they don't necessarily have. So but because it's a relatively new city, you can think of it as a bunch of baby robbers, right? Who want to forge money. They want to, really stick it to the government and say, like, we own the government, we make our own money, right? So because they're babies, they don't really know what money look like. So what they're going to do is they're going to generate a bunch of things that look like that. So, naturally, right? They're babies, so they make all these scribbles, and it's like, okay, maybe this is money, okay? So they distribute it to the department stores, to the medical clinics, and everywhere. And because the workers of those medical clinics and department stores are also babies, so they don't know. So that money gets circulated around, and the baby cops come and pick it up, and they say, oh, look, I've got some real money, I've got some fake money, maybe. So the cops are trying to differentiate between the real money and the fake money. Because they're babies, they don't know the difference between the two either. So what they're going to do? But surprisingly, there's a special twist in the story where there's a police chief who's not a baby, who's actually an adult and knows what he's doing. And he tells the baby to say, okay, what's real and what's fake? So he will give them a bunch of examples. The baby will show the police chief some examples and say, this is real money, this is fake money. And the baby cops will say, oh, yeah, okay, I kind of get the difference now. Not really, but, you know, because they're babies. But over time, you can think of them as like, okay, I can kind of see the difference between, you know, having a face here and whatever that is. And so, you know, the cops are happy. They know kind of what money is and what a bunch of scribbles is, and then they go to bed. But late at night, a secret informant from the police brings this information that the police know. Aha! They say. The baby says, the really mischievous baby says, I know what the police knows now, so I'm going to feed it to the robbers what the police know, the difference between the scribbles and the money. And then the robbers will be able to do, like, you know, look at, oh, okay, now they know that we need a face in the middle. So they're going to start drawing a face in the scribble. Something like that. So the circle goes around and around and around until the babies and the cops grow up and they grow into adulthood, and then they think, at one point, basically the story concludes in such a way that at one point, the cops really don't know the difference between real money and fake money because they look so similar, and the robbers, because they feed off the information of the secret informant, they don't know, the secret informant doesn't know the difference either. So the robbers have no more information to generate any other new fake money. So in the end, you're going to get a bunch of money that looks like real money. And the sad ending is that the robbers win here, not the cops. So bit of a nightmare for most of us, I guess. But so that's the idea, right? So we iterate over and over and over, looking at real things and fake things. One side of the model will try to discern between fake and real money or whatever, and the other side will try to generate even better fakes, right? So based on the information that they got, and this sort of circle goes on and goes on and goes on until we are able to generate some real-looking things. Okay, so we have two people, well, a bunch of people to thank for this technology, generative adversarial networks, particularly these two guys, Ian Goodfellow and Joshua Bengio from the University of Toronto, somewhere in Canada. So they came up with GAN, which is basically this idea that you can approximate some sort of data distribution by running it through these networks that kind of fight each other, right? So because we have there's these bunch of police guys and these bunch of kiddies, they fight against each other, creating more and more fakes and being more and more adept at telling apart fakes. So in the end, you have this model that can generate things by having, you know, two networks fight each other, which is, I think, quite an interesting idea to behold in itself. Particularly, we're going to look at an extension of GAN, which is called DC GAN, or Deep Convolution GANs. So this is like the prototype visual of a GAN. So you have this something called latent random variable. You can think of it as like the thoughts that appear in your head on how to form things, and then that goes into a generator, which is a convolutional neural network. Well, we should say transpose convolutional neural network, because from this vector of noise, we want to create an image that is 2D, right? So it has to go through some convolutional step, and then we sample from that generator, and at the same time, we also sample from real-world images. So these are the fakes, and these are the real, and then the cops here will try and discriminate between real or fake, and then we have a loss function at the end, which I'm going to discuss a bit more at the end. So, like I said, GANs have many variants. One of them that we're going to use today is DC GANs. Right now, the state of the art that was published, I think, a couple of months ago, I think in August 2018, is Big GAN, and it's basically a super optimized version of the GANs that we've had, and they're able to generate very real-looking images. Maybe I can show you some at the end. I don't have them in the slide, but some context would be nice. State of the art is Big GAN right now. DC GAN is a bit 2016 but it's easy to understand and produce. So that's what we're going to do. So the data set. So how are we going to come about getting a bunch of Pokemon? Well, we scraped them, right? So I took, I went to some website and just pulled out a bunch of images of Pokemon. I trained it on that small set for a bit, on like the 807 official art or something like that, and it wasn't great. So I took to the games as well to pull out the sprites, and I trained on a bit, and it was still okay, but not great. So I took another run at pulling in the shinies. So a shiny Pokemon is like a color shifted version of a Pokemon. So think of like a Pokemon that's blue suddenly becoming like green or something. So so we exclude unknowns, which are these really regular shaped things, and they really mess the data up and doesn't allow you to create very nice looking Pokemon. You end up with like these circular Pokemon with dots in the middle, which is a bit weird. But yeah, so I'll upload this data set after the talk. I have it on my Dropbox, but I'll put it up on like an S3 on my website or something, so you guys can play around with it too. Yeah, so that's the scraping. The pre-processing is to put a white background on it. Ideally, we want black background because black is 0 in numerical terms, and that doesn't feed information into the neural net as much, and so the neural net would have an easier time trying to figure out which things are actually Pokemon. But that's a bit too hard to do because you have to do image segmentation, so I went with a white background because it's just like, you just paste it on a white background, which is easy. So I fuzz crop to center, so these images sometimes were like very big with the Pokemon in the middle, so I had to like crop that. I use a fuzz crop, which just fuzzily finds edges and stuff and just crops to that bounding box. And then I resize it to 64 by 64 pixels because I have a 1050 Ti, which is 4 gigabytes of memory, not a lot in my lab. So I have to work with limited memory, so small image sizes were the go-to. And we have it changed from, well, RGB is usually defined from 0 to 255 in 3 channels, so we move it to -1 to 1 for stability and for ease of training. So there's a normalization that you do, which makes it easy for training. That's a bit technical, so I won't go through that. I also do random horizontal flips, so like, just flip the image like that, because, well, gravity is downwards. If you flip it upside, you'll get Pokemon that are upside down. We don't want that either. But you can, if you flip a guy around, you can kind of tell it's the same guy sort of thing. So that's what I did. So Pokegon, what I'm going to talk about is the structure of the net itself. This is V8 because I did 8 iterations of this. I spent most of my weekends in front of my computer, clearly. So the generator starts with a 100-dimensional noise vector. So think of it as like an array of just random numbers. We sample from random Gaussian noise because Gaussian noise is stable. As opposed to uniform noise, which is kind of scattered everywhere. So because Gaussian noise stays within the bell curve, most of the values are very close to 0. We have 4 transpose convolutions. So think of them as rather than convolutions down into some representation space, you want to convolve from representation space into image space, right? So 4 of those. 1, 2, 3, 4, and then batch norm each of them, and then ReLUs all the way until tan h at the end. So if you remember 2 slides ago, I said from 1 to -1 here. Oops, sorry about that. From 1 to -1. So tan h will do that. We'll threshold it from -1 to 1 for the output images. So that's how the generator is done. The discriminator is the opposite way. So think of it as like the dark generator sort of thing. So input image is a 64 by 3. You have 4 convolutions, so you're going from image space to representation space. We do batch norm again, ReLUs all the way, but this time it's sigmoid because we want to be able to discern between fake or real. So because the labels are binary, 0 or 1, sigmoid works here just fine. Okay. Next is the loss function. So the discriminator needs to be able to decide what's real or fake. So we feed the actual images, the real images, with label 1, plus some uniform noise. This is from the guy who created PyTorch. He advised when doing GAN, you should add some noise to the label, so it's not a hard label sort of thing. It's like a soft label, so the gradient descents are not like jumping, rather it's like sloping down. And we fake images with 0 with uniform noise, and we use cross entropy loss on the sigmoid, so it decides between 1 and 0 for the discriminator, and when back propagation happens, the discriminator only updates knowing this. The generator needs to convince itself it's generating real images, so we feed the generator fake images but with label 1, so it thinks that it's creating real images, and then we propagate the error through the discriminator and into the generator. So the discriminator only backprops from the output of the label 1 or 0 into the discriminator, but the generator has to go through the discriminator and into the generator, right? So I think about 6 slides ago we had that. So the discriminator, the loss is propagated through the model and updates the weights in here, but the generator has to propagate the loss through the discriminator and into the generator. So that's like the secret informant sort of technique, right? So you go from the loss through the police station and then into the criminal's HQ. All right. So that's the loss function, and the optimization we use Adam, which is created by Khalifa. We use a tiny learning rate for V8 because it's really unstable, especially for the images of Pokemon for some reason. Maybe, I don't know, Ganscape Pokemon or something. We set beta 1 equals 0.5 because this is based on the DC GAN paper. It's very stable too, and beta 2 is 0.9. So we get a faster descent rather than 0.99, which takes a bit longer. Okay, so we can look at code. So if you guys have laptops, I have an example of the code running in Colab. So if you guys go to that link, give a couple of minutes for you guys if anyone wants to have a look at the code. If not, then we'll proceed. All right. Everybody ready? Yeah? If you're not, then just maybe borrow the link from a friend or something, or there's no board here. Yikes. Okay. If you're good at memorizing letters and numbers, please get that into your head right now. I'm going to switch really quickly to Colab. So yeah, I've got it training right now. I was hoping it would come up with something, but we can step through the code really quickly. Yeah, so, oh, anyone used Colab before? Yeah, okay, one guy. So Colab is a pretty cool thing. So you can run a bunch of Python code without installing Python into your computer, which I think is pretty awesome. And you also get a GPU system. Right? You can go to runtime up here if you're on your laptop. Change runtime type, and then you can go for hardware acceleration, GPU. TPU you can use, but you have to do some heavy lifting before that, so I don't recommend to use it yet. So yeah, you can use GPU. Is that why it's training so slow? Because it's on CPU. Huh. Okay. I'll switch to GPU so we can step through the code. Okay. So now I switched to a GPU instance, so it's going to reload everything. So basically the code just goes and download the files from my Dropbox and then extract it. And then we port TensorFlow and enable eager execution. Oh, did I miss a slide? Yeah, I think I missed a slide. Where are we? Yeah, eager execution. Okay, you know what? I'll explain this later because it's a minor thing. Okay. Yeah. So we import TensorFlow here. Here. Yeah. And then some more inputs here. Imports, not too important. So here's the image parsing function. Okay, I know there are some like weird numbers there, so pardon me because I was trying another thing last night. So don't worry about the text there up there. And then we start with the image parsing function. So we just decode the PNG because we have a bunch of PNG. We convert it down to float, and then we resize it to 64 by 64. With Google Colab, you can do these nice form things. So rather than editing the code here and finding the variables that you want, you just go to this form over on the right side, and then you can press whatever 109. Sorry. Change the value and then rerun the cell, and you get your new values, and it works just fine. While we're talking about this, I'm just going to run it very quickly, so we have some outputs. Okay, so yeah, dataset configuration. So this just says load this into a dataset that is a generator, so we don't have to manually iterate through it. And then we should be able to see some Pokemon show up here. So this cell just prints out the Pokemon images. Please? So it takes a while. If you're familiar with like the Jupyter Notebook sort of environment, this is very, very similar. Here we go. So these are like some images. I think I uploaded the wrong data set into my Dropbox, so we have unknowns and we have black backgrounds. They're all supposed to be white. I'll upload the right one later on. Yeah, sorry, I had last night to pull all of this stuff from my hard drive. And then let's look at the generator model. So it's written with Keras, because Keras is now kind of merged with TensorFlow and it's easy to work with. So we just have a transpose convolution, a batch norm transfer convolution, batch norm convolution, batch norm convolution, batch norm. And then we just do conf, batch norm, relu, conf, batch norm, relu, blah, blah, blah. Yeah, so this sort of generator code uses eager execution, so that means the graph that you're working with is dynamic, but you can have the option to freeze the graph later to make it static. You get a performance increase as well for each epoch, because with dynamic graphs, it's kind of like an open-ended problem, so TensorFlow will try to optimize it in some way, but if you freeze it and say like the graph is like this, then it will have some performance increases. And then tanh at the end, right there. Okay, the discriminator model is here, which is the opposite. Like I said, it's like the anti-generator, conf, batch norm, conf, batch norm, conf, batch norm, and then fully connected layer at the end, which is then also added with the sigmoid loss later. So yeah, so yeah, not much to talk about here, but you can probably see, or maybe not, but you can probably guess that the numbers grow smaller in this side, times 8, times 4, times 2, times 1. So because we are convolving from representation space into image space, we need a high dimensional representation going down to image space. And in the discriminator, we get the opposite, basically, from a small image representation, image space into representation space. So growing bigger, 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 having more and more features to learn. All right. And then we freeze the graph, which is what we're doing here, to make it faster. And then we define our losses. The discriminator loss, like I said, is a bunch of ones minus some noise, and then the loss is a sigmoid cross entropy. Similar to the fake ones, you get a label of 0, pardon me, and random uniform plus 0.2. So you get these soft labels rather than the hard 1, 0 labels. With the generator loss, we don't do that. Again, this is like the GAN hacks that people do for for image training. Sometimes it works, sometimes it doesn't. Sometimes you have to play with it. The initializer are optimizers for the discriminator and the generator, which is the same parameters, with the exception of beta 2, which is kept at 0.9. And then these are some boilerplate code, not necessarily generating training images. So this is the training block itself. So with TensorFlow, TensorFlow eager execution, you get the gradient, the auto gradient differentiator. So the code can run in a loop, but when you do backwards, when you do backprop, it just follows along the tape and it just like rewinds the tape. So you can think of doing an operation as, you know, pressing play on a cassette tape. If people remember cassette tapes, I'm from that generation. Yes, so if you press play on a cassette tape, it will roll, and then you'll get some information coming in. And then when you say backward, or in this case gradient, it will rewind the tape, but rewinding will differentiate at each block. And because we have ultra differentiators becoming more and more common nowadays, so it takes the automatic gradient of each operation down into the weights, and that's when we apply the gradient here down there. This is pretty cool because in cases like recurrent neural networks, where the information is fed back into itself over and over and over, you can now do it with a for loop and not have the consequences of, you know, the graph breaking because it's dynamic, which I think is pretty cool because you don't have to flatten out a recurrent neural network into a static network, but rather you can have this for loop which goes even in different numbers of times. So imagine like sequencing, or sorry, not sequencing, predicting a name which has 7 or 12 or 15 characters. You might have to run for loop 7, 13, or 15 times, but your neural net is not limited to 7 times or 15 times or 13 times. You can run it as many times as you want. And I thought that was pretty cool to feature that TensorFlow now has. Okay, the rest is boilerplate code again. You can find more information in the links that I've kind of littered everywhere on the document. And training failed. That's a shame. Why? 16 by 100. Expected 4 dimensions. Ay, ay, ay. Okay, I might have changed something or somewhere. Not a problem. I'll fix this, and you guys, I'll put this up on my website. You guys can check it out later. Like I said, one night does not allow for a lot of errors. You guys are probably hungry to see some outputs, so I'll let you. Yeah, so I've explained TensorFlow eager execution as I went along. So this is how I started with the whole thing. So my very first try, I had the hard labels, 1s and 0s, standard Adam, no, I didn't change the learning rate, I didn't change beta 1, beta 2, no image preprocessing, I just took it as it is. 100 epochs, max pooling in the network. So max pool is another way to shrink down images. But in the network that I use strident convolutions to pool down the images. So I had max pooling enabled the first time, and I had a fully connected noise to convolution 1, which is actually a bad idea because you get images that look like this, like this, like this. Yes. So I did no pre-processing here, and you get like a cloud of mess and like disappointment. So I took back, went back to the drawing board. So I tried a second try. Well, hard label still. Changed Adam with 0.5 beta 1. Maybe it's stable there. Tried misspelled. Blanking the background, so I tried changing some of the background colors. 200 epochs this time, max pooling enabled, but no more fully connected noise layer. And it looks something like this. Okay, thank you very much. So like some of the backgrounds are now black, just now they were like colored backgrounds and stuff. And even then, I still got cloudy mess. So I kind of like, went through this, looked at this, went back into the drawing board and kept iterating. After this, I kind of forgot where I went, but I kept all the images of each run. So this is run number 3. Sorry about that. Yeah, so still same, and I think I tuned a bit of the parameters, and now you're starting to see some structure. I think that the training was maybe a bit longer, or changed like more convolution layers, something of that nature. So you can start to see things like arms and legs and like tail and something. Okay, that's a mess. So but it's a bit a win and lose. And then I took off the black background, and it started to become more stable. But in these cases, I still had the unknowns, which are those things. So you have things appearing like circles with dots in the middle, and yeah, they don't really look like Pokemon at all. And towards the end, I think this is my most recent run. No, this is like the 3rd one. So I kept going back, and this is the last one. Yeah, so this is the last one. I took out all the unknowns. I reparameterized everything, and you can look at the setup in GAN V8 slide. But basically, now you have a bunch of Pokemon that kind of look like Pokemon. Well, they have more like more structure in the end. So like this guy or this guy has like eyes kind of, and so the network's very shallow, right, to generate images. So ideally, if you had like a ResNet or something really deep, you could get really good results. Of course, the training time would take hours and hours. I mean, one run on my GPU took about 7 to 8 hours for 300 or 400 epochs. So it takes a while to get results on this sort of thing, especially if you're doing it on weekends. But I have Sumit Chintala, the creator of PyTorch, to thank for this, because he provided all these list of hacks, which I kind of iterated through. So the images, the fake images, getting better is as a result of applying more and more hacks into the network. And I guess this is a testament to hacking works sort of thing. So there you go. Some good outputs. So I want to share some of the ones that I think I'm quite proud of. So I scattered them everywhere, but there's a guy like holding a flame, sort of. This is like legs, and then there's like wings at the back. This is like a really sad dinosaur, and this is like a fox if you really squint. That guy's kind of like doing a matrixy thing. That's kind of like a bull. And, you can kind of imagine these things to be realish, but yeah, these are the ones that came out pretty well, and quite proud of the network to be able to do this. And I only trained this about 400 epochs, so not a long time. 400 runs through the entire data set, which has about 16,000 images, I think. Yeah. So I guess it's your turn to play around with this whole thing. I think GANs is a very fun side of things. It doesn't just work on images; it works on text, it works on audio, works on spectral analysis data, anything. So, but of course, it's a generative model which has not much use in the real world in some sense. So you can think of some use cases for generated data, like noise-generated data, but in the end, it's mainly fun. I've got some data sets, so I wanted to do, I have some banknotes data set, like pictures of money, which is why that whole money, that whole money story came about. I thought I was going to do it with money, but Google Colab is a bit slow. The GPU is a bit backed up, and you only have it for like 12 hours max or something. So I couldn't get a good money-looking GAN. So I went back to my Pokemon. I have some Elder Scrolls names if you guys want that. That's on my website too. So go crazy. If you have some interesting ideas, go ahead. GANs is always a fun thing to do.